Hi guys, I miss you. So this is probably even more awkward for me than it is for you because yeah, I'm shy and awkward and British and this is way outside my comfort zone, so bear with me. So we've been working chapter 6 in class. We already did section 6.1 and 6.2. I've included them in your notes for completeness. You may want to review that because it's been a weird kind of couple of weeks. We've been away and stuff, we might have forgotten. So we were talking about wave particle duality of matter and what that means in terms of electrons only being able to exist in quantized energy levels. So we see these visible spectra of atoms and oh yeah, we set things on fire. That was fun, right? Good times. So when we see the ground state, that corresponds to the lowest energy configuration of those electrons in their quantized energy levels. And then when they are excited, either by passing electricity through them, setting on fire, some form of exciting the electrons by giving them energy, they go up into higher energy configurations, and that's when we see those visible spectra. So the next step then is where are these electrons? They're in what we call orbitals, which is not like that traditional shell model that you may have learned in high school, but it's an area of three-dimensional space, a probability distribution where the electron is probably located, and these come straight out of solving the Schrödinger wave equation, which I will not make you do, but basically the idea is three quantum numbers describe where that electron is in three-dimensional space. So the three quantum numbers are the principal quantum number, n, so that's the energy level, what we may colloquially call the shell. Then the angular momentum quantum number, which is L, that describes the shape, so we often call that the subshell. And then the magnetic quantum number, which is M subscript L, and that's the orientation, so what we'd call the specific orbital. So going back to the angular momentum quantum number, for each number value of L, we have a letter name. So if L is 0, that is our S, L is 1 is our p orbital, L is 2 is D, and L is 3 is F. These come from spectral line names, so they've been around forever. So S is sharp, P is principal, D is diffuse, and F is fundamental. You don't need to know that, but you know, it might make it easier to remember the letters. So what do they look like? The s orbitals are spherical and they have nodes within them. So that is corresponding to the principal quantum number. There's n minus 1 node in each s orbital, and a node is an area where there's zero electron density, so the probability of finding an electron there goes to 0. The p orbitals kind of look like dumbbells, and there's 3 of them, which are degenerate. That means they have the same energy. So this is where the ml, the magnetic quantum number, comes in with the different orientations. So for p orbitals you have px, py, and pz, and that literally means the dumbbell is aligned along the x-axis, the y-axis, or the z-axis if we're talking about Cartesian axes. Same deal with the d electrons, the d orbitals. There's 5 different orientations of the d orbitals, and those are like double dumbbell shapes. So like the xy, the yz, the xz, those are in between, the lobes are in between those Cartesian axes. And then the x squared minus y squared, the lobes are on the x and y axes, and the z squared, the lobes are along the z axis. So the dz squared is the one that's a little bit different because it's like a single dumbbell, like a P, but it's got stuck in a donut, so it's got like a rubber ring around the belly, so that's the odd one out. There's 7 f orbitals. You don't need to be able to draw them. I don't even know if I can draw them. They're tricky. So then we move on to like how the electrons fill up these orbitals, so what we call writing electron configurations. So basically, like any kind of energy considerations, the electrons are going to be in the lowest energy orbital first, right? That's called the Aufbau principle. So electrons are going to occupy the lowest energy orbital available to them first. They're going to occupy them with parallel spins. Okay, so each electron is either spinning clockwise or anti-clockwise. So we call this like spin up or spin down to differentiate between them. That's Hund's rule. So they will singly occupy parallel spins in the lowest energy level until all the lowest energy orbitals have 1 electron in them with parallel spin. And then they're going to have to pair up before they can occupy higher energy orbitals. Remember, we're looking for the lowest energy configuration at all times. So when they pair up, they will pair up with opposite spins, okay? So that's called the Pauli exclusion principle, and we have to kind of make up a 4th quantum number for this. It doesn't come from the Schrodinger wave equation. It's just to bodge it and make it fit. So this is m subscript s, okay, the spin quantum number, and it's either +1/2 or -1/2. Okay, so when we're talking about writing electronic configuration of ions, cations lose electrons to form a positively charged cation, and anions gain electrons, okay, to fill up that outer shell, and then they form a negatively charged anion. So size-wise, cations are always going to be smaller than the atoms that they came from, and anions are always going to be a little bit bigger. So we can start to explain the periodic trends that we see in terms of atomic radii and ionization energies based on what we know about the electronic structure, where the electrons actually are, okay? So it all comes back to the internal electronic structure. So as far as atomic radius goes, as we go across a period, we're adding electrons to the same shell, the same n value, right? The same distance from the nucleus, right? So yes, the nuclear charge, the atomic number Z, is increasing, but because the electrons we're adding at the same distance from the nucleus, they're going to, as you add more and more electrons, they're going to experience increased nuclear charge, okay? We call that effective nuclear charge, or Z subscript F. So they're held slightly more tighter, which corresponds to a slight decrease in atomic radius. Similarly, as you go down a group, okay, as you're going down each level of the group, you're adding an extra shell, an extra n value, n equals 1, n equals 3, etc. So that means the outermost electrons are further away from the nucleus. So the outermost negative charge is further away from the positive charge that they're attracted to, so they're going to be held less tightly. And there's more stuff in between that negative charge, the outermost electrons, and the inner positive charge in the nucleus, right? So it's just going to get bigger and bigger because it's held in less tightly by that positive charge. And it's the same argument for the trends in ionization energy. So ionization energy is how much energy it costs to take an electron away to form a cation. So as you go across a period, again, that increased nuclear charge as you go across is going to make it harder to remove a negative charge, okay? So it's going to be held in more tightly by the positive charge of the nucleus with increased effective nuclear charge. So the ionization energy is going to get higher across a period, which makes sense, right? When you look at the periodic table, metals are on the left, they form cations, anions are on the right. Non-metals on the right, they form anions, okay? So that makes sense with that trend, right? Similarly, as you go down a group, you're adding more and more shells. So the outermost electron that you're trying to remove is further from the nucleus, feeling less effective nuclear charge. It is shielded by all the stuff, i.e. electrons, in between the outermost electron and the nucleus. Therefore, it's going to be easier to remove because it's held less tightly by that positive charge of the nucleus. So that's pretty much all you have to learn for chapter 6. That's the important stuff, okay? So make sure I'm still going to have availability during our normal lecture times of 9 to 9:50. I'll be on Zoom. I will try and manage that as best as I can, depending on how many people turn up. I will also record those sessions, so if you can't get in there, if technology says no, you will at least be able to access the wisdom of my discussions with whoever does turn up. Equally, I'll have my office hours at the usual times: Tuesday 9:30 to 10:30 a.m, Friday to 2 to 2:50 p.m, all on Zoom. You can find links directly to the meeting under the Zoom tab in ReggieNet. I will not record office hours, okay, and I may have to use breakout rooms depending on how many people to turn up to kind of triage, and if people want to talk to me privately, etc., I'll try and make that work. If you need to contact me for any reason, just email me, right? I have my emails come to my phone. I can catch up to you straight away, okay? And of course I can always do, if you can't make my office hours, etc., I can always do meetings with you by appointment using Zoom, of course. Okay, so take care, check in with you again soon. Bye.